Hello everyone, in this presentation we will introduce MProtoNet, a case-based interpretable deep learning model for brain tumor classification. This is the joint work of the University of British Columbia and the Southern University of Science and Technology. Deep learning models have achieved state-of-the-art results in many fields, including medical imaging, but their interpretability has always been an unresolved issue. Deep learning models such as CNNs often learn undesired shortcuts during training, and medical settings have higher requirements for verifying the evidence used to make predictions. Interpretable deep learning models can be divided into two categories, post-hoc explainers and interpretable by design models. Post-hoc explainers such as GradCam have been criticized for being unreliable and undifferentiable because they are not part of the model design. As for the types of explanations, heat map-based explanations are the most widely used, but they can only provide localization information. Concept-based explanations require predefined concepts, while case-based explanations use prototypes identified from training image patches. MProtoNet is a pioneering work on case-based deep learning models. The network makes predictions by comparing similarities between the input image patches and the identified prototypes, providing both heat map-based and case-based explanations. Each class has its own prototypes, which are randomly initialized during training. Relying on cluster and separation loss functions, training image patches are centered around prototypes in the embedding space, similar to clustering algorithms. Case-based deep learning models are very suitable for medical imaging applications, but their current usage is limited. The original authors of MProtoNet applied it to breast lesion classification, but they found that MProtoNet had difficulty locating the lesion region without using fine-grained annotations. However, fine-grained annotations are particularly expensive for medical imaging, especially for 3D images. MProtoNet uses a specially designed attention module to generate heat maps and locate disease regions, and fine-grained annotations are optional. However, there is no evaluation of interpretability metrics, which is critical for interpretable models. In this work, we propose the medical prototype network, MProtoNet, to extend MProtoNet to 3D MPMRIs. A new attention module with soft masking and online cam loss is introduced. MProtoNet achieves statistically significant improvements in the interpretability metrics of both correctness and localization coherence without fine-grained annotations during training. The source code is available on GitHub. We used the publicly available BRATS 2020 dataset, which contains 369 subjects with pathologically confirmed diagnoses. Each subject has 4 modalities as well as the segmentation labels for evaluation of interpretability metrics during testing. This is the overall architecture of MProtoNet. It consists of 4 layers, a feature layer with 3D ResNet as the backbone, a localization layer with add-on and mapping modules, a prototype layer, and a classification layer. At a high level, MProtoNet makes predictions by comparing processed features with a set of learned prototypes. The feature layer uses the 3D version of ResNet 152 as the backbone and is trained from scratch. During training, we follow the online data augmentation pipeline of NNUNet to overcome the limited size issue of the training data. The mapping module of the localization layer is modified from MProtoNet and outputs attention maps for localizing regions related to prototypes. To learn more accurate attention maps and reduce irrelevant background areas, we introduce differentiable soft masking to sharpen the values of the attention maps. In addition to soft masking, an online cam loss is proposed to assist localization of the attention maps by directly utilizing image-level labels during training. To obtain class predictions directly from intermediate features, we choose LSE pooling, which has better convergence and localization performance. In our experiments, we use the balanced accuracy to evaluate the classification performance on the imbalanced dataset. For the interpretability metrics, we use the incremental deletion score to measure the correctness of reflecting the decision-making process of the model, and the activation precision to measure the localization coherence with the fine annotated label. For classification performance, there are no statistically significant differences among all models. The complete version MProtoNet C achieves the best performance in the interpretability metrics of both correctness and localization coherence, showing that both soft masking and the online cam loss are very important for statistically significant improvements over MProtoNet. These visualization examples clearly show the improvement of MProtoNet C over all other models in terms of localization coherence. This demonstration of the case-based reasoning shows that MProtoNet can provide case-based prototypical explanations with both attention maps and similarity scores. There are potential directions for future improvements. First, a dynamic or shared assignment of prototypes may be more suitable for some applications. Second, we can also test fusing the modalities at the end to analyze each modality individually. Finally, combinations with other interpretable methods such as concept-based models will be very interesting. That's all, thank you.